So you have rampant side effects all through your code, mutable state everywhere, and enter functional programming to help you solve these problems. So I'm a dev at REA, and while there I've worked both on some of our functional stuff in Scala and also in our Ruby areas, and I've seen quite a few problems in some of our Ruby stuff that can be addressed by taking some of the techniques that we use in our functional apps. And from this talk, you should get an idea of what's really the core of functional programming and parts that you can apply when you're not necessarily working in a functional language, how you can use it in projects you're already working on, not just shiny new greenfields projects, and that it's not very hard and complicated, and that although neckbeards are welcome, they are not required. So we'll talk about immutability, putting off side effects, referential transparency, some common traps that people make when explaining it, and where you can go to learn some more about it. And all of it, to me, really comes back to stopping things from changing behind my back in unexpected ways, making it all very clear so I can reason about it and see what's going on. So we'll start with immutability, which is when you don't change any values. Instead, you create new ones. You only use constants. So you use recursion and accumulators over loops and mutation. And any confusion that you've had over whether you're passing by value or passing by reference is gone because it's not getting changed. And if you've ever thought about whether you'd use a bang when you were reversing a list or something like that, that was thinking about mutation. And sometimes mutation can be extremely confusing. In one case, I was working on the build of an older Java app. We had to add a new build task to some contract testing. So we had, in Gradle, you have this global list of build dependencies. We needed to do a thing to the one we introduced. So we filtered out the one we needed, did our thing on it, ran our task. It worked. Our contract test passed. So then we went to run the full build. It did not work. So we got all these weird dependency missing errors and things nowhere near what we had touched. So we took a look at what changes we'd made, and there was this, nothing that looked particularly suspicious, but there was this filter. And then when we debugged it, we realized that filter in Groovy actually mutates the list. So we'd gone and deleted every other build dependency other than the one we were trying to use. And I have an example of when, so we're trying to total a shopping cart, and both a mutable and immutable approach to do that. So we're working on this item class that just has a cost because it doesn't need anything else for this example. So a straightforward mutable solution could be to just make a total, iterate through everything in the list, and just add it to the total. Oh, did they? Okay. And a recursive immutable solution, this is a bit of a more verbose one that's more explicit, would involve having a base case, which is here, which is when the recursion stops and it starts returning, and a recursive case where it calls itself again. So in this example, we take a list and we get the head and the tail to separate them out using the split operator, which is what you'd normally do when doing a recursive function on lists. Our base case is when the tail is empty, we just want to return the cost of the item. And in the other case, we want to take the cost and then total the rest of the list. However, this way is quite verbose. It's actually more verbose than the mutable solution, and it's not as clear as would be ideal. So we can also do pretty much the same thing with implicit recursion, using higher order functions, which is functions that take functions as arguments or return functions. So in this case, it runs this function, the total plus item. Okay. It runs this function on every item in the list. It goes through each item, and it has an accumulator that's called total that starts out at 0 because that's what we supply it with, and then it's added to every time. And you may have also seen the inject function is pretty much doing what the example above does, just internally. And you may have also seen inject called fold in other languages. And moving on to side effects. So what are they? It's whenever your code does stuff that affects the outside world. So it's really the reason you're writing your program. Whenever you say print something, write something to disk, do a network call, that's a side effect. It's what your program does. But in functional, we like to make them explicit and separate them from the logic. So we have a core that has all the logic and generates a representation of the side effects, and then an edge that actually does the side effects. So that core is really easy to see what it's doing, to reason about, and to test, and then we can put off the side effects until the edge. And it makes the core easier to deal with, and the outside is still a bit difficult, but at least it's quite separated. I don't think it likes me. So now we have a new requirement for our shopping cart example. We have to print out the result of the total. So a straightforward side affecting solution, non-functional solution, would be just to chuck logger.info on at the end and print out the result. It's very simple. A functional solution would be to just leave what we already have as it is, but to add in another function that calls it and then prints the result. So the total cart function is our functional core in our tiny little system, and print total cart is our outer edge. And right now it looks a bit more complicated to use the functional solution, but when you look at the tests, it pulls ahead quite a lot. So to test the generation of the total, not testing the side effects in this example, for the one with the side effects all mangled in with it, we have to do doubles, and the tests are less clear with the intention. We have to expect the object to receive a thing and then call the function, so it's not as explicit what we're expecting to be done, and we're having to use dependency injection and the doubles to make it work, and it's a lot more verbose. Most of us have probably seen some examples that get a lot more complicated with a lot more doubles than this, just to get it actually tested, and then it's unclear and not always so sure that it's testing what it should. But if we look at the test for the functional example, it's so much clearer. We don't need any of the doubles. We just have call the function, check the output is what we expect. It's much clearer to see the intention, and it's much briefer. And moving on from that, when you combine immutability and no side effects, you get referential transparency. So you can call a function again and again and again, and you just get the same result, and it causes no harm, no side effects. Which means you can substitute the result that you've saved for the call, or the other way around. So you can just think about the value you saved as what you put into it, not what you've put into it and then this, and then that other thing, and every other thing that's happened to it. And it means that everything the function does is shown by the result. You don't have anything unexpected going on. And an example for that one, say a transparent example where we're just printing out the reverse of a list repeatedly, it will do the same thing. We have the same line of code, one after the other, and it does the same thing. Seems pretty reasonable. However, if we mutate, in this case, by using reverse bang, which changes the string A, then the same line of code, in pretty much the same place, does different things, which can be surprising in other cases. And when you're thinking about A on line 10, you need to think about A and all the things that have happened to A, which in a larger system can be a big long list of things that have happened to A. And when teaching FP, there are some common pitfalls, which I expect quite a few of you will have seen. A common one is to get too mathematical. I'm quite guilty of this. When I was preparing this talk, I initially had an example that was a number sequence, and I said not to get too mathematical. Taking my own advice so well there. And it's important to relate it to things they already know. For example, with monads, a lot of people have used them but they don't know the word. And I've had great success explaining them without ever saying the word monad until they understand it. And because of the very academic image that FP has, it's important to focus on the practicality and examples and make it clear that it's not just for academia, that you can do real-world stuff in it, and fight misconceptions like that we have no side effects rather than just isolating them. And there are some places you can go to learn more. Unfortunately, I couldn't find much in the way of materials for doing it in Ruby. But there are some online courses that I'd recommend, and these are also in this, you can also get these in the slides that are on GitHub. So there's an online course, there's a book I suggest. If you're wondering what a monad is, then Refactoring Ruby with Monads is a really good talk that should explain it quite well. There's some functional training in Scala, functional training in Haskell, and the slides for this itself. Are there any questions?
You mentioned referential transparency, and it was clear that that implies idempotency. But are they the same thing, or is there any difference between them?
I'm not sure, sorry.
Anyone else?
Oh, there's another one there.
Might you attempt a monad explanation?
Sorry, what was that?
Might you attempt a monad explanation?
If people are interested in learning what monads are, I recommend they look at the Refactoring Ruby with Monads talk. I wasn't going to have the time to fit that into this talk as well as explaining the fundamentals, but that talk's really good, so I recommend it. But I would not be surprised if you've already used them without knowing. They're not actually that hard.
Cool. Anyone else?
Hello, I'm not sure whether you were here yesterday morning, but I was wondering if you had any comments about how it would interact with the talk yesterday on the event sourcing.
Yes, so that was about using immutability, so that does relate, so that's useful for storing your things. So you can either store the diff or you can make new things, and that's for storing the diff approach.
Hi. Are there static analysis tools that you benefit from when you use FP that we probably can't take advantage of in more dynamic languages?
So when I've done most of my experience with functional is with static types, and I did find that more useful, and some things have been an uphill battle when I've tried to do them in a dynamic language like Ruby. So it does help. The static types can constrain your potential solutions further, and in some functional languages like Haskell, you're constrained to keeping it purely functional, so it constrains out things that you probably don't want to do if you're trying to do functional.
Cool. Anyone else?
But I don't think that the Ruby static analysis tools don't check for, say, are you being purely functional? Maybe someone could write one, but I don't think there's one now.
Cool. That being the case, thank you so much.
Thank you. And if you have any follow-up, you can come and look for me or email me. We're also hiring at REA, so you can come and talk to me or other people and go to the website. And I'd like to just go back to what it really means to me, which is stopping things from changing behind my back.